Hello everybody, welcome back to another video, and in this video we'll be looking at the derivative of e to the x using first principles. So what we'll be doing is we'll be looking at the derivative of e to the x using first principles. And we know that from my very first video of this channel, and one of the most fundamental ideas in calculus is the first principles formula, which is we know that some f prime of x, the derivative of some function, is going to be equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. And another thing that we'll need to know is the definition of e, because we have the derivative e to the x, so it might be useful to know what the definition of e as the constant is. So we know that e can be defined as the limit as, let's say we have some n going to infinity of, and then we have 1 plus 1 over n, and this is all raised to the nth power, like so. So with these prerequisite pieces of information, let's get started. So we will use first principles. So now we have to use, so this is going to be equal to the limit as h goes to 0 of f of x plus h. F of x plus h, f of x is e to the x, so f of x plus h is going to be e to the x plus h. And let's just put a bracket here to show that this is all the function part of the limit. And then we subtract e to the x, because e to the x is our f of x, and that's all over h. Now we know that as part of a very basic index law, when we have a to the power of n multiplied by a to the power of m, that's equal to a to the power of n plus m. So what we can do is we can use the reverse of this idea to break down this exponential here into, so now we have the limit as h goes to 0 of, and then we can write this as a product of e to the x and e to the h, because we know that if we add the exponents we get exactly what we have here. So then here we have minus f of x, e to the x all over h. Now what we see is that we have an e to the x in both terms, so why don't we try factoring that out? And what we also notice that's pretty cool is that the e to the x term is independent of the limit here. So what we'll see is that, so we'll just write this down. This is the limit as h goes to 0 of, and then we have e to the x factored out here, and we can write that as e to the x minus multiplied by, and then we have e to the h minus 1 now, because if we factored out e to the x we would get this minus 1 and then all over h, and this is the same thing because we're multiplying it. And what we see here is that we can actually bring this e to the x outside of the limit, because we know that this e to the x does not have any h in it, which means that this will be completely unaffected by this variable. And if we have the limit of some variable approaching to some constant, and or some infinity, and we have inside of that function something that does not contain that variable that is changing, we can just leave it as it is. So what we have here now is just e to the x now brought out times the limit as h goes to 0 of e to the h minus 1 all over h. And this is the big limit that we're trying to evaluate in today's video, because once we evaluate this we will get the answer. So, and of course, if you know the derivative of e to the x, which we should all know by now, we should know what this limit immediately evaluates to. But how do we get there in the first place? That is the fun part. So what do we need to do? What we need to do here is some, well, first thing that we can do is we can perform a substitution. We can perform a u substitution where, let's say we have u, and let's say that's equal to the numerator, which is e to the h minus 1. Then, of course, we find du, which is taking the derivative of e to the h minus 1, and then solve for dh. Okay, that was a joke. This is not related to integrals, and to avoid any confusion, this is just simply an algebraic substitution. So what we're doing here is we just need to account for what the variable u now is approaching, because what we're trying to do is just bring this to the u world to simplify some things, because this integral on its own is in indeterminate form. If we plug 0 into this and 0 into this, we see that e to the 0 is 1, 1 minus 1 is 0, 0 over 0, that's indeterminate. And of course, we cannot do L'Hopital's rule because we need to know the derivative of e to the h, which is what we're trying to do. So avoid that circular reasoning there. So what are we doing? In algebraic substitution, so u is e to the h minus 1, let's say. Now, we need to see that u is approaching. And how do we calculate what u is approaching now? Because we can't have this h is approaching in the limit. So what we see here is all we need to do is we need to just plug in what h is approaching into this substitution. So we see that e to the 0 is, of course, 1, and 1 minus 1 is 0. So u is also approaching 0, which is pretty nice. And the second thing we need to do is we see that we have a h here, which is uninvited. So we need to solve for h. So first of all, let's add 1 on both sides. So we get u plus 1 is e to the h. And how do we solve for h? Well, taking the natural log of e to the something will return that something, of course, because by definition, the natural log of e is 1. So here we have the natural log of u plus 1 is h. So we can bring this to the u world now. And once again, this is an algebraic substitution, so no derivatives going on here. So we have the limit now is u is going to 0. And our function now, our numerator is just our u, and that's all over. And then here we have h, which is ln of u plus 1. And now you may ask, why did you do this? So the key idea that we see here is that if we have some a over b, some fraction a over b, so let's just do that over here. We know that a over b is also equal to the reciprocal of the reciprocal. And how do we take the reciprocal? Well, we take 1 over that. So, and also, what is the reciprocal? That is flipping the fractions. So if we flip the fractions once, that is not the same. But if we take the reciprocal of that, take 1 over that, we do have a set of equivalent fractions here. 1 over b over a is the same thing as a over b. So we'll use that key idea here, and we'll write this as e to the x multiplied by the limit as u goes to 0 of 1 over, and we have now, we just flip the fractions. We have the natural log of u plus 1 over u. And we see that this indeed is the same thing. And what we can do is we, of course, if we have some a over b, just very small point here, we know that's 1 over b times a. Just to illustrate the concept here so that we can apply this with more complicated examples. So here, we can write this over u as 1 over u multiplied by. So we have this e to the x times the limit as u is going to 0 of 1 over. Then we have 1 over u multiplied by the natural log of u plus 1, like so. And what do we see here? Well, we know the property of logarithms is that if we have some RL ln x, or by that matter any base for the logarithm, but we can just take r ln x, that's equal to the natural log of x to the r. And x to the r, that note is the function inside of the natural log is raised to the r power, not the natural log itself. So what do we see here? We have something multiplied by a natural log. So guess what we can do? We can bring this to the exponent. So this is e to the x multiplied by the limit as u is going to 0 of, and we have 1 over now. So we have 1 over, and we have the natural log of, and then we have now u plus 1 to the 1 over u's power. You've brought that to the exponent. And what we see here, that something is very interesting, is that first of all, we can take this limit inside of this function because, well, first of all, we know the limit of a quotient is the limit of each quotient. And what we see here is that this 1, of course, is unaffected. So what we'll actually get is we'll get e to the x multiplied by 1 over the limit as u goes to 0 of the natural log of 1 of u. I'll write this as 1 plus u to the 1 over u's power. That's all in the natural log, like so. And what we see here is that if we have the limit of a function, and that function is continuous over like this, over this interval, then what we see here is that we can actually swap the function and the limit. So the limit of the function is the same thing as the function of the limit. So this is equal to e to the x multiplied by 1 over the function, which is the natural log of the limit as u goes to 0 of, and then we have 1 plus u, we have here 1 plus u to the 1 over u's power, like so. And what I will say here, and just close that bracket here, is that this limit right here evaluates to something very nice. And that is where we need to go back to our definition of E. And let's just quickly grab our definition of e and bring it down there. And we'll see that there's some kind of resemblance between these two limits. So what do we see here? Well, we see that we have 1 plus u to the 1 over u, and here we have 1 plus 1 over n to the n. Those look pretty similar. Why don't we try substitution? Why do we say that some n now, doing another algebraic substitution, is, let's say n is 1 over u, and now we need to figure out what n is approaching. So to do that, we plug in what u is approaching into this substitution. So 1 over 0, and 1 over 0 is approaching infinity. So n will actually be approaching infinity now. And what we see here is that we can take this limit to the n world now. So we have e to the x multiplied by the limit of 1 over the natural log of the limit as n now is going to infinity of 1 plus, and then u. To solve for u, we take the reciprocal of both sides. We see that u is 1 over n, so 1 over n. And that is being raised to the 1 over u power. And what is 1 over u? That is n. And what we see here is that 1 plus 1 over n to the n, as n goes to infinity, that is exactly what our definition of e is. And this is where we see that this limit right here is the alternate definition for e as well. Because by performing this substitution, seeing that 1 over 0 does approach infinity, we see that these limits are equivalent. So all we see is that this limit right here is e. So all we have is now e to the x multiplied by 1 over, and then we have the natural log of this limit evaluated to e. And of course, the natural log of e is 1. So this is equal to e to the x multiplied by 1 over 1, and that is equal to e to the x. So therefore, we see that the derivative of e to the x, like so, is equal to e to the x, and then we can put a box like so, which is very, very cool. So that is it for today's video. Here just a recap. We use the first principles to find the derivative of e to the x, and we used two substitutions here and saw that we stumbled upon an alternate definition for e. So thank you for watching.